Everybody, we are finishing out chapter 5 today, so covering these two sections, 5.7 and 5.8, talking about the roots and zeros of the polynomial. So looking at the first example, it says to consider the graph of the polynomial that is graphed to the left for you. Okay, so it's already graphed out for you, but they just want you to identify the zeros to this function. So again, we're just looking for where is it crossing over the x-axis. So there's obviously 4 of them, so we're just identifying those 4 spots. Let me get my marker going. Okay, so again, the 4 spots we're looking at would be right here, right here, right here, right here. So just identify those zeros from left to right. Looks like it's crossing at -3, at -2, at +1, and then also at +2. So that would be all my zeros. Okay, so doing the same thing, we want to solve each of the following polynomial equations by factoring. So just kind of reviewing our factoring skills. Looking at the first one, for factoring, you can take out a GCF from all 3 of those terms to start. So 2, 16, 32, you could definitely take out a 2. With the x's, you could take out 2 x's from each term. So if you divide out your GCF, you would be left with x squared plus 8x plus 16. And now, obviously, trinomial is still factorable. So if you're thinking about what multiplies b 16 and adds b 8, that'd be 4 and 4. So completely factored, here's what you would have. Okay, so now we want to solve it. So solving this from left to right, again, starting with the GCF, set 2x squared equal to 0, and then since you have 2x plus 4s, you could just set one of them equal to 0 because they obviously give you the same answer. But 2x squared equal to 0, to actually solve it, you can go through, start getting x by itself, divide both sides by 2. Well, that's still 0. Taking the square root, you get x equals 0. Okay, so there's one answer. And then the second one, again, since these are the same, you get the same answer twice. Just subtract the 4 and you get x equals -4. Okay, the next one, solving by factoring. Let's see, there's no GCF between all 4, but since I do have 4 terms, I just want to factor by grouping. So in my first grouping, taking out the GCF, that'd be x squared. I have x plus 2 left over. Second grouping, take out -4, where again you'd have x plus 2 left over. So since these match, bring together again your 2 GCFs, x squared minus 4, followed by just one of the pairings of x plus 2. But your 2 GCFs that came together, the x squared minus 4, that's a difference of squares. You can still keep on factoring. So if I keep factoring x squared minus 4, that'd be x minus 2x plus 2. And then we have the x plus 2 from the factoring by grouping. Okay, so now solving. So setting each one equal to 0, starting with x minus 2. And again, just like the last problem, since we have 2 of these, all you have to do is just list down one of them. And then solving it, we get x equals +2 and x equals -2. Okay, there's our solutions. And for number 3, last one, so bring the 29x squared over, just subtract it. So you'd have x to the 4th minus 29x squared plus 100 equals 0. And now we're set to factor. Okay, so again, just like a normal trinomial, I'm just trying to find what multiplies via 100 and adds to be -29. This factors into x squared minus 25 and x squared minus 4. So 25 times 4, that's 100. And then if it's -25, -4, that will give me -29. Okay, but these are both a difference of squares, so keep on factoring. Breaking it all the way down, you'd have x minus 5x plus 5 for the first difference of squares, and then x minus 2x plus 2 for the second one. So solving from left to right, you get x equals 5, x equals -5, x equals 2, and then x equals -2. Okay, this is leading us into our first conversation here. So with the first couple problems at least, we did see the same answer more than once. Okay, this is what's known as being the multiplicity. So what the multiplicity is, it's basically you're listing out the number of times a number is a solution. So like I said, we get the same answer more than once. Let me just even backtrack here to the first problem. We actually have 2 answers of 0. Technically, we get 2 answers of 0. So the multiplicity here would be 2, because we have 2 answers of 0. And then same thing with the -4, since we had 2 of the same binomial of x plus 4, we also have a multiplicity of 2, because we get the same answer twice. So there's technically 4 answers altogether, but we get both answers 2 times. Okay, same thing for the next one for number 2 that we did. Since we had the same binomial twice of x plus 2, we technically have a multiplicity of 2 for the answer of negative 2, but we have a multiplicity of only 1 for positive 2. And then over here, obviously we just have each answer 1 time, so each multiplicity would just be 1. Okay, but if you get the answer more than 1 time, your multiplicity would be depending on how many times you have that answer. Okay? Moving on to what's called the rational root theorem. So it says P over Q. This is just listing out the possible rational zeros. So it's not actually finding the zeros. It's just saying what are my possible solutions. That's all it is. So what is P? What is Q? What am I doing here? It's kind of highlighted for you, but P is always your constant, and then Q is always your leading coefficient. So it's P over Q. That would make this then 9 over 2, P over Q. And how you're going to list out the possible zeros, you're just going to be listing out the factors of each number. So if I'm talking about 9 on top, think about what multiplies to be 9. Well, positive and negative 1 with positive and negative 9, right? 1 times 9 will give me 9, but it could be positive, could be negative, along with positive and negative 3. Those are all the factors of 9. And then factors of 2 would be plus and minus 1 and plus and minus 2. Okay, so here's all my factors. Here's how you list out the actual possible zeros now. So you're going to start with plus and minus. You want to list out all the factors in the numerator over all the factors of the denominator individually. So just even starting with the 1 over 1, let me kind of highlight what I'm doing. So 1 over 1, which is obviously just 1, and then doing 3 over 1, so that'd be plus and minus 3, followed by plus and minus, now you want to do 9 over 1, so that's plus and minus 9. Okay, now you want to do all the numbers on top over 2. So listing out more numbers, now I'm doing plus and minus 1 over 2, so plus and minus 1/2, and then we'd have plus and minus 3 over 2, so 3 over 2, and then plus and minus 9 over 2. So these are all my possible solutions to this problem. Okay, we're not saying that these are the answers, but as far as my rational, real solutions go, these are all my possible solutions. Okay, so now doing the same thing, we're just going to use the rational root theorem. We just want to list out where the possible solutions to the problem. Okay, possible rational zeros. So go back here, I like blue better. So just identifying P and Q. P and Q. So my constant, which is 24, over leading coefficient, which is 1. Honestly, it doesn't matter if you say 24 or negative 24 because they have the same exact factors anyways. So if I list out the factors of 24 or negative 24, again, they're going to be the same. So think about, again, what multiplies to be 24. Starting with the basics, 1, and then obviously 2 goes into there. 3, 4, not 5, but 6, 8. So we got 4 times 6. 3 times 8, 2 would go with 12, and then we also have 24. So kind of going to the next problem, looks like. And then the bottom, the only factors of 1 is obviously just 1 times 1, so positive and negative 1. So listing out the possible zeros, well, all these numbers on top are just going to be over 1, so just make it now into an actual list. So we're just doing 1 over 1, so plus and minus 1, plus and minus 2 over 1, so 2, plus and minus 3, plus and minus 4, positive and negative 6, positive negative 8, positive negative 12, positive negative 24. So these are all the possible, real, rational solutions to the problem. Okay? So for the next one, same thing. P over Q would be 16 over 2. Okay? So now listing out all the possible, rational, real solutions. List out the factors. So that'd be 1, 2, 4, 8, and 16. On bottom, it's just 1 and 2. Okay, so now make your actual list. Again, all the numbers on top over 1, all the numbers on top over 2. So you'd have plus and minus 1 over 1, 2 over 1, 4 over 1, 8 over 1, 16 over 1. And now going back, putting them all over 2 now. So you'd have plus and minus 1/2. Followed by, when you do the next one though, plus and minus 2 over 2. Well, 2 over 2 is just 1, which we already have that listed up here. So you don't have to do that one again. And then same thing with the next one. 4 over 2, well, that's just going to be 2 when you reduce it. So we don't have to do that one. 8 over 2, that's just 4 again. Don't have to do that. 16 over 2, that'd be 8 again. So this actually is going to complete our list. Okay, so when you reduce down the answer, if you already have it listed out previously, then you don't have to list it again. Okay, the last one, number 6. So P over Q, that'd be 12 over 3. Now start listing out the factors. So that's 1, 2, 3, 4, 6, and 12. Bottom, that's just 1 and 3. Okay, so now listing out the possible zeros. So we'd have plus and minus 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. Okay, so there's everything over 1. So now putting them all over 3, you'd have plus and minus 1 over 3, 2 over 3, 3 over 3 we can skip, because again, that's just 1. Plus and minus 4 over 3. 6 over 3 we don't need, because that's just going to be 2. And 12 over 3, that's just 4 again. So here completes my list. There's all my possible real rational solutions. All right, so moving on to the next page. So that again was the rational root theorem. Now we have the irrational root theorem, which basically just says this. It says that irrational roots will come in conjugate pairs. So breaking this down, irrational. Typically that means you just have a radical left over in your answer, and we should know what a conjugate it is by now. But here's kind of a little example I have. So if I have, let's say 2 plus the square root of 7 as a solution, automatically its conjugate is going to be an answer 2. So these always come together as conjugate pairs. Or if I had, negative square root 5 as a solution, then I'm also going to have positive square root 5. Those are conjugates. Okay, so we're going to see that kind of play out here too when we get through some of these examples at the bottom. But in the next example, we're kind of putting it all together. Okay, use the rational root theorem, it says, to identify the possible rational roots. Then test the possible roots to find one that is actually going to be a root. You can use synthetic substitution for this. Factor and find the remaining roots. Okay, so we want to find all the roots to this problem. But first, list out what are the possible roots. Okay, so P over Q, that's 12 over 1. So we're going to start with that. Okay, listing out the factors, we got 1, 2, 3, 4, 6, and 12. Bottom, that's just 1. Okay, so the actual list would just be plus and minus 1, 2, 3, 4, 6, and 12, since they're all over 1. And now we have to actually start testing these and find one that works. So it looks like already kind of set up for you. They put positive 1 inside the box, setting up for synthetic. So how I'm going to know if 1 actually works, if it's going to be a solution, is I'm checking to see, do I get a remainder? Okay, if I don't get a remainder, then that's a good sign. I can say that yes, that number is going to be a solution. But if I get a remainder, if I get anything besides 0 as my remainder, then I have to move on to something else. Try the next possible solution. Okay, but we know the possible solutions. Now start testing them. Okay, so starting with positive 1, we're going to test and see if that one works. So dropping down your coefficients, 1, negative 3, negative 4, 12. Again, we're really just checking for this part here. Do we get a remainder? So the 1 just drops down. Multiplying is 1, adding is negative 2. Multiplying is negative 2, adding is negative 6. Multiplying is negative 6, that's a no-go. Okay, so I can rule out positive 1 is not a solution. So maybe you'd want to try negative 1 next, since again it's positive and negative 1, but it looks like they want us to try positive 2 now. So positive 2 is inside the box, so let's go ahead and set it up. 1, negative 3, negative 4, 12. All right, check and see again, do we get a remainder? So 1 drops down. Multiplying is 2, adding is negative 1. Multiplying is negative 2, adding is negative 6. Multiplying is negative 12. Bingo. There we go. We got one solution. Okay, so we have one answer so far out of the 3 solutions that we should have. But one answer we know for sure is that x equals positive 2, since positive 2 did work over here in the box. Okay, how you're going to find the other solutions? You want to take what you have left here, which is 1x squared minus 1x minus 6, and now you just want to factor what you have left. So I'm just trying to figure out what multiplies be negative 6 and adds be negative 1, which is negative 3 and positive 2. So we get x minus 3, x plus 2 is how it factors. And now solving each one, set each one equal to 0. Set each factor equal to 0. Solving now, x would also be positive 3, and x would also be negative 2. So we can add that over here in the box. We also found positive 3 and negative 2. These are all my roots to the problem. Okay, so if we were to actually graph out this polynomial function, we would see it crossing over the x-axis in all three of these spots, positive 2, positive 3, and negative 2. Okay, those are all my x-intercepts. All right? But you can see this process could get quite tedious. You know, you might be going through your list over here. It might take you all the way down to 6 until you actually find a solution. Okay, so I'm going to show you guys another way to do this too using the calculator. That'll hopefully be a little bit more helpful. All right, but trying the next one. Again, list out the possible solutions first just so you have an idea. What are my possible solutions? So P over Q. So that's 1 and 3 on top, and then 1 and 2 on bottom. So really not too many possibles. There'll be plus and minus 1, plus and minus 3, plus and minus 1/2, and then plus and minus 3/2. Okay, there's my possible real rational solutions. But here's the quicker way to find these, okay, using the calculator. If you type this in, let's go to table, type in your function that we have here. So we have 2x cubed. Actually, I should probably clear that one out. Okay, so 2 again, x cubed, followed by minus 5x squared. So minus 5x squared, minus 4x, and then plus 3. So if I type this into my table, hit enter, I'm going to start again at 0. That's always just a good starting point. Go down to OK. And now looking for, you're trying to find now an x-intercept. So how do you know what an x-intercept is? Well, you should know what an ordered pair of an x-intercept looks like. It's when x is a number and y is 0. So you're really kind of looking in your second column. You want to scroll through and try to find a good 0. There's one right there, positive 3. Okay, I know for sure from my table that positive 3 is a solution, which it's listed out as a possible over here. So in your possible list, you can see plus and minus 3 is a possible solution. But again, looking at your table, you know positive 3 works. Okay, so you already have one answer so far. You already know that x equals positive 3 to this problem. But we still have to find the other solutions. Okay, so at least we have one of them. So take 3. Let's do synthetic division. So 2, negative 5, negative 4, and 3. But since we know 3 is a solution, then that should mean you should definitely not get a remainder. Okay, but going through, 2 just drops down. Multiplying would be 6. Adding would be 1. Multiplying is 3. Adding is negative 1. Multiplying would be negative 3. And boom, look at that. Again, no remainder. Okay, with what you have left over here now, you're going to want to go through and actually factor it. So what you have left is 2x squared plus 1x minus 1. Now we have to factor this by guessing and checking, which isn't too bad. Since 2 is a prime number, has to be obviously 2x and 1x. And then multiplying to be negative 1, well, that obviously has to be 1 times 1. And now we're trying to, again, when we FOIL it, we want that 1x in the middle that we see, positive 1x. So complete answer, how's this going to factor? Let's see. This would have to be a plus, this would have to be a minus. Okay, so completing it out now, I have it all factored. Now solving, set 2x minus 1 equal to 0, set x plus 1 equal to 0, and solving for your last remaining answers. If you add 1, divide by 2, you would have 1/2, and then subtracting 1, you get negative 1. So to complete my list, we found 3 from the calculator. Now we also know positive 1/2 and negative 1 are also solutions. So basically, if I go back here to my calculator, if I go up instead of down like I did, if I go up into the negatives, there it is right there. Negative 1, 0 is another 0 that we could have used. Okay, so we could have also used that one instead. So instead of dividing with 3, we could have divided with negative 1 instead. All right? But I will let you guys use the calculator if that will help you to at least get one of the zeros. Okay? Just get one of them, but I still want to see the factoring process and everything else. All right, so moving on to the next one. So again, listing out the possibles to start. So P over Q, so that's 4 over 1. You have plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 1. So possibles would be plus and minus 1, plus and minus 2, plus and minus 4. Okay, here's my possibles. Again, if you want to, You can pull it up in the calculator. So I'm just going to go ahead and type this in. So going back to table, we'll clear that function out, and I'm just going to type in starting with x cubed, and then we have minus 6x squared, and then we have plus 6x plus 4. Okay, go ahead and hit enter. Again, I like to start at 0, just a happy medium. Going down to OK. All right, looks like I see one already. So I can already see this 0 right here, positive 2, 0. That is an x-intercept. Okay, so as you can see too, it's already listed out over here as a possible, but now I know for sure that x equals 2. So there is one solution, x equals 2. So now for the rest of it, so dividing 2 into 1, negative 6, 6, and 4, synthetic division again, you should not get a remainder. Okay, so the 1 just drops down. Multiplying is 2, adding is negative 4, multiplying is negative 8, and then adding would be negative 2, multiplying is negative 4, no remainder. Okay. Now take what you have left, which is 1x squared minus 4x minus 2. And now we have to try to factor this. Well, even looking at it, with that middle number being bigger than your c term, so just thinking about what multiplies to be negative 2, the same two numbers have to add to be negative 4. Well, the only numbers that multiply to be 2 are 1 times 2. There is no way, shape, or form I can get a negative 4 out of that with those two numbers. So clearly it's not factorable. So how else can I solve this problem? Well, if I can't factor it, what else you could do is you could use the quadratic formula. Or you can even do completing the square if you like completing the square better. I like the quadratic formula. It just kind of seems to always work. You always have the formula provided to you. So I'm just going to plug this into the quadratic. Okay? So 1 is our A, negative 4 is our B, and then negative 2 is our C. I'm just going to do it down here in problem number 11, plug it into the quadratic. Okay? So if I plug this all in, I would have x equals starting with negative b, so negative negative 4, plus and minus square root of b squared, negative 4 squared, minus 4 times a times c, and this is all over 2 times a. All right, here we go, quadratic formula, fun stuff. So we're going to have positive 4 plus and minus square root, that'd be 16 for negative 4 squared. And now negative 4 times 1 times negative 2 is positive 8. This would be all over 2. Okay, next, 16 plus 8, we would have 4 plus and minus, that's 24 underneath the radical now. And now simplifying the radical, if you simplify the square root of 24, that's going to be 4 plus and minus, that would just be 2 square root 6, all over 2. And the last and final thing is you can reduce this now. So all those numbers out front, the 4, the 2, and the 2, divide everything down by 2. So your last two answers here would be 2 plus and minus 1 square root 6, or just square root 6. Okay, so as I already illustrated to you, you can actually see the irrational root theorem in play here. As we mentioned up above at the top of this page, irrational solutions, irrational roots always come in conjugate pairs, and you could see that right now. Okay, from the quadratic formula, these are conjugates, 2 plus square root 6, and then 2 minus square root 6. Okay, they come in conjugate pairs every single time. So if you already have one irrational root, automatically its conjugate should be an answer as well. All right, so let's try one more. We'll try number 10, then we'll move on to the next page. So for number 10 again, listing out the possibles. So P over Q, that'd be 12 over 1. So I'm just going to go ahead and start listing them since I know they're just over 1. So it'll be plus and minus 1, plus and minus 2, plus and minus 3. We got 4, 6, and 12. So here's my possibles, but now we have to actually find them. Okay, so again, if you want, I'm going to go ahead and type this into the calculator. So let me clear this out. Clear, clear, clear. Okay, so from table, from the y equals, go ahead and type in, we got x to the 4th. So we got a big one this time, x to the 4th. Okay, get out of there. So you have plus 2x cubed. Get out of there. Minus 7x squared. And then we have minus 8x plus 12. Okay, so once it's all typed in again, just hit enter. Starting at 0, that sounds good. Go down to OK. Hit enter. Look, there's 2 of them right now. So you pick and choose whichever one you'd like to use. I'm just going to use positive 1. And technically, since we do see two of them, we can use both of them. Okay, I can show you guys how to use both roots as well. But I'm just going to start with positive 1. Okay, we see two answers right now, but I'm definitely going to start with 1. Okay, so 1 goes inside the box. We got 1, 2, negative 7, negative 8, and 12. Again, we should not get a remainder since we know it's a solution. So 1 drops down, multiplying is 1, adding is 3, multiplying is 3, that'd be negative 4, negative 4, negative 12, multiplying is negative 12, no remainder. Okay. So right here, even at this step, if you want, you could stop and factor, okay, find the remaining solutions, which we obviously know that 2 is another solution, right? But what you can also do, since we know those two roots, I can take what I have left here and do synthetic again, now with positive 2. So I'm going to take this answer, that 1, 3, negative 4, negative 12, and do synthetic round 2. Okay, maybe I'll use a different color so it stands out a little bit more. But the 1 would drop down, multiplying would be 2, adding would be 5, multiplying is 10, adding would be 6, multiplying would be 12, and again, no remainder. Okay, so again, I have two answers. I have 1 and 2 so far. Now take what you have left here. Well, we did synthetic twice. Keep that in mind. So we started with x to the 4th. So right here, that would have been x cubed. So now I'm down to 1x squared plus 5x plus 6. And now I have to factor and solve for my last remaining answers. So factoring this, what multiplies these 6 adds to be 5. That's definitely going to be 3 and 2. So 3 times 2 is 6, 3 plus 2 is 5. And now solving for the last one, set x plus 3 equal to 0, x plus 2 equal to 0. And our last solutions we get x equals negative 3, and x also equals negative 2. So negative 3 and negative 2, there's all of your solutions. So again, even if we scrolled up instead, if we went up, look at right there, negative 2, negative 3, there's all the roots right there. Okay, but again, we still definitely want to see some of the work. You're not always going to have all the solutions right there in the calculator, so you still have to know the whole entire process. Okay, so there you go. All right, there's finding all the roots. So basically, if you can't factor something initially, so like in number 10, there's no way, shape, or form you can factor this original polynomial. Okay, there's no way I can solve that by factoring. So we have to go through this process in order to actually break it down to get to something that is factorable. Okay, to solve for the remaining zeros. Or even if it's not factorable, like you saw back here in problem number 9, right, that wasn't factorable. I had to use a quadratic formula. All right, but moving on to the next part. So in this next page, it says, filling in all these blanks, that you have a real number r is going to be a 0 of the polynomial equation p of x equals 0. So I should even state too at the top, it says all these statements are equivalent. So these all mean the same thing. Every single bullet point that I'm explaining here, they're saying the same thing over and over again, just in a different way. Okay, so there's the first one. The second one says p of r is 0. So basically, if you plug in this answer, plug in that number for the polynomial into x, then you will get 0. R is an x-intercept of the graph of p of x equals 0. The next says that x minus r is a factor of the polynomial p of x equal to 0. When you divide, on this next one, when you divide the rule for p of x, if I divide that by x minus r, the remainder is 0. And it should be, right? So to actually prove that it's a root, the remainder should be 0. Last one says that r is a solution of p of x equals 0. So again, these all mean the same thing. I'm saying the same thing over and over again, just in all different ways. Okay? Now, what we're going to do is to write the simplest polynomial function with the given zeros. We kind of did something like this in chapter 4 where you have the zeros and you have to work it backwards, find the original polynomial. So again, we know right now that x is negative 2, x is 2, and x is 4. These are the solutions, right? We have to write the simplest polynomial function with these given zeros. So work it backwards. You want to set each of these equal to 0. So working it backwards, that would mean I'd have to add 2 to equal that one to 0. I'd have to subtract 2 to equal that to 0, and then subtract the 4. Now you're going to take these polynomials, or these binomials rather, you're going to multiply them. So multiplying these together, if I have x plus 2 times x minus 2, times x minus 4. That will give me the original polynomial that these roots came from. Okay, so let's just even start with the first two. If I just FOIL these two together, I'd have x squared minus 2x plus 2x minus 4. So these obviously cancel. Minus 2x plus 2x, I just have x squared minus 4. So there's my quotient from the first two. Now I'm going to take that answer and multiply it with what we still have over here is x minus 4. Now multiply those two together. So foiling those two out, you would have x cubed minus 4x squared minus 4x plus 16. So here's the original polynomial, okay, that those roots came from. So same thing for number 2 right next to it. Again, you have these roots. You know that x equals 0. You know x equals 2/3. You know that x equals 3. So x equals 0, what is equal to 0? So x by itself is going to be one of the factors. With the fraction, again, you got to break this up into 2 steps. First, just multiply by the denominator to cancel the 3. So you'd have 3x equals 2. And then subtract the 2. So it's 3x minus 2 equals 0. Okay, there's my other factor. The last one, set this equal to 0. Just move the 3, subtract it. So it's x minus 3. Okay, so here's what we're multiplying. We got the x. We got 3x minus 2. Then we have x minus 3. I would probably, as my game plan, I would probably FOIL those two binomials and then just distribute the 3 once it's all said and done. So if we FOIL these two together, we'd have 3x squared minus 9x minus 2x plus 6. So we get 3x squared, that'd be minus 11x plus 6. And now just take that x from the very beginning and just distribute it to all 3 terms. So if you distribute that inside, you'd have 3x cubed minus 11x squared plus 6x, and that'd be your solution. Okay, same thing for 3. I'll just kind of talk about it briefly, but we have that x equals -2, x equals 1/2, and x equals 2. So work it backwards, add the 2, set it equal to 0. This would just be 2x minus 1, and this would be x minus 2. So you would take x plus 2, 2x minus 1, and x minus 2, and multiply these all together. Okay, answer you should get, I'll just kind of skip through this one, but you should get 2x cubed, once it's all said and done, minus 1x squared, minus 8x plus 4. And there's the original polynomial. Okay, but I want to move on to the fundamental theorem of algebra, which it's corollary. These two honestly kind of say the same thing, so I'm just going to kind of lump this together. It's something we've already talked about before, and I'm sure your other teachers have talked about it with you, but now we have an official name to it. It's the fundamental theorem of algebra. It says that the degree, just kind of in my own words too, but the degree of the polynomial tells you how many roots. So again, remember what roots are. Roots are going to be the same thing as saying the zeros, which is the same thing as the x-intercepts, which is the same thing as saying the solutions. So the degree of the polynomial is going to tell you how many solutions that you will have. Okay? So solving this equation, finding all the roots. Next example, remember all the steps again from 6.5. From 6.5. From the previous section. Sorry, that's a typo up here. So we don't want to talk about 6.5. So that's from just the previous section, basically what we just got done doing. So first thing you want to do again is you want to list out the possibles, right? So P over Q. So 20 over 1. So again, since they're all over 1, that would just be plus and minus 1, 2, 4, 5, 10, and 20. Here's all the possible solutions, but now we want to actually find them. So again, what I would do first, I'm going to type this in so I can just find at least one root to work with. So if we type this in, go into table, clear that one out. So we have starting with x to the 4th, okay, followed by plus 4x cubed, and then we have minus x squared plus 16x minus 20. All right, there it is. Hit enter. Again, I will start at 0, go down to OK, All right, there's one right smack dab in front of my face, positive 1. Okay, so I'm definitely know that x equals 1. That's definitely one solution. So now find the other solution. So take 1, again, doing synthetic division, setting it up. We should not have a remainder. So 1 drops down, multiplying is 1, adding is 5, multiplying is 5, adding is 4, multiplying would be 4, adding is 20, multiplying is 20, and then we have no remainder. Okay, so what we have left now is 1x cubed plus 5x squared plus 4x plus 20. Now take this and factor it. Okay, to factor, since we have 4 terms, we'd have to group it. So take out the GCF between the first two, which is x squared. Got x plus 5 left over. GCF the next one would be positive 4, where you also have x plus 5 left over, so that's good, right? These are matching. So 2 GCFs come together, x squared plus 4, and then x plus 5. Okay, so now we have to solve for our remaining zeros. And again, keep in mind, the degree tells us how many answers we should have. We should have 4. We have 1 so far. Okay, positive 1 came from the calculator. But now solving each of these, set them equal to 0, set x squared plus 4 equal to 0, and set x plus 5 equal to 0. So now just subtracting 5, that's easy enough, negative 5. So there's another solution. On top, just subtract the 4, and then square root it, where you get plus and minus 2i. So you get positive and negative 2i. There's all 4 solutions. Okay, positive 1, negative 5, positive 2i, negative 2i. There's everything. So moving on to the next page. And on the next page, doing the same thing over again. So listing out the possible solutions for 36, there's quite a few of them. I'll just kind of go ahead and skip ahead. I'll let you guys know. The one that I found in the calculator was negative 1 to use. So if we do negative 1, going through doing synthetic, you'd have 1, negative 3, 5, negative 27, negative 36. All right, so we have left here, 1 drops down, multiplying is negative 1, that'd be negative 4, positive 4, 9, negative 9, negative 36, positive 36, and then no remainder. Okay, so we have left, so again, we have one answer so far, x equals negative 1. That came from the calculator. And now find the other solutions. We should have 4 altogether, but we have 1x cubed minus 4x squared plus 9x minus 36 equals 0. And now factor by grouping again, 4 terms. So first grouping, take out an x squared. You'd have x minus 4. Second grouping, take out a 9. And again, you'd have x minus 4. These are matching. So now GCFs come together, x squared plus 9, along with x minus 4. And now solving each of these. Okay, so set these both equal to 0. I'm going to set x squared plus 9 equal to 0. Along with x minus 4. That one's easy, just add the 4. So you also get positive 4. And then subtracting 9, taking the square root, you get plus and minus 3i. And there's all 4 solutions. Okay? This last one here, you can do the whole calculator thing, find a solution, again, from your possibles, but you can actually completely factor it. So even right from the very beginning, I can just factor and find all 3 solutions right from the very beginning. So if I just factor by grouping, take out the GCF, x squared, I have x minus 3, take out positive 4, again I get x minus 3. Bring your 2 GCFs together, x squared plus 4 with x minus 3, now just solve it. So for 3 answers, set x squared plus 4 equal to 0, along with x minus 3. So if you subtract the 4, take the square root, you get plus and minus 2i. That's 2 solutions. Add the 3, get x equals positive 3. So there's all 3 answers. Okay, and as you've kind of noticed, the complex conjugate root theorem, so complex means basically imaginary. Conjugate, again, we know what conjugates are, and then root theorem, well, roots are just the solutions. So same thing as the irrational root theorem, same idea. When you have a complex solution, these come in conjugate pairs. So complex solutions will come in conjugate pairs. So whenever you have an imaginary solution, its conjugate is automatically a solution as well. So if I divide up, like the previous problem, if I divide up these two answers, I'd have positive 2y, and I'd also have negative 2y. Those are conjugates, right? So they always come together as pairs, those two together. So the last part of today is to find the missing zeros and then also write the simplest polynomial function with the given zeros. So for number 7, they're saying that these are the solutions. We know that x equals 4i and x equals 2. Well, the missing zero would be the conjugate of 4i. Negative 4i is also going to be a solution automatically. Okay, so this rule only applies to complex solutions along with irrational. Okay, so this would be all of my solutions to the problem. For number 8, if I know that negative square root 5 is a solution, well, positive square root 5 should also be a solution, but we also know that x equals 3. Okay, and the last one, we know that x equals 2 plus i, so we should also have 2 minus i as a solution. We know that x equals square root 3, so that means that negative square root 3 should be a solution, and we know that x equals 1. So it only applies, like I said, to irrational numbers and also to imaginary. Okay? If you want to write the simplest polynomial function with these zeros, what you'd want to do is quite a process, but again, equal these all to 0. So even looking at the first one, if I want to equal this to 0, I'd have x minus 4i equals 0. So there's one binomial. I'd also have x plus 4i equal to 0, and then I'd have x minus 2. So you'd want to take, again, all three of these, x minus 4i, x plus 4i, and then x minus 2, you'd want to multiply them together. So you just want to start foiling. Okay, so I'll do the first one. You guys can do the other ones if you'd like to. But if you multiply these two together, let's just start with these first two. So I'd have x squared. This would be, what, x 4i. And then this would be minus x 4i. So these just cancel, basically. And then negative 4i times 4i is negative 16i squared. So we have x squared minus 16i squared. Keep in mind, I squared, that's just negative 1. So this would just be x squared plus 16, because negative 16 times negative 1 is positive 16. Okay, so I'm going to take this now, take this quotient. Now we have to multiply that by x minus 2. So multiplying these together, this would be x cubed minus 2x squared plus 16x minus 32. And there's your complete solution. Okay, so if you wanted to do the other ones, you can. Feel free. Knock your socks off. But for the next one, what you should get as the answer, I'll just write it up here. You should get x cubed minus 3x squared minus 5x plus 15. And the big one, the last one, what you should get if you FOIL this all out and multiply it together. Let's see. Do I have my final answer? You should get x the fifth minus 5x the fourth plus 6x to the third plus 10x squared minus 27x plus 15. So that's the entire polynomial. So honestly, that would probably take up almost a half sheet of paper if you were to go through and actually multiply it all out. The last one, though, application problem. A grain silo is in the shape of a cylinder with a hemisphere top. The cylinder is 20 feet tall. The volume of the silo is 2,106 pi cubic feet. Find the radius of the silo. Okay, well, first of all, they're talking about what? Volume? Okay, so the volume of the entire silo we know is 2,106 pi cubic feet, but you have to know how to find the volume of each shape. Okay, if you're talking about the volume of the cylinder at the bottom, well, that's pi r squared h. And then the hemisphere on top, the volume is 2/3 pi r cubed. Okay, so again, the total volume we know is 2,106 pi, and that's equal to the sum of these two together. So the hemisphere, the volume of the hemisphere, along with the volume of the cylinder. Okay, we do have some type of measurement. Again, we're solving for, it says to find the radius, so we're solving for r, but we at least know the height of the cylinder. So we're going to take 20, we're going to plug that into h, okay, along the way. So we would have 2/3 pi r cubed plus pi r squared 20. Okay, so here's what we got so far. Next thing I'm going to do is I'm just going to rewrite that last term just so it looks nicer. So 2/3 pi r cubed plus, I'm just going to write this as being 20 pi r squared instead. But next thing I'm going to do is I'm going to set this equal to 0. So I'm going to subtract the 2106 pi to the other side. So we'd have 2/3 pi r cubed plus 20 pi r squared minus 2106 pi equals 0. Okay, next thing I'm going to do is I'm going to go through and divide everything by pi. If you notice, every single term has a pi in it. If you divide every term by pi, you'd have 2/3 r cubed plus 20r squared minus 2106 equals 0. Okay, makes it a little bit nicer. Now, going through, solving it, again, you could type this into your calculator. We're just trying to find a solution. Okay, what could the radius possibly be? What the answer comes out to? You could try to factor it as well. Factoring I don't think would work too well, so it looks like you probably have to use a calculator for this one, but what you should get in the end, r comes out to being 9 feet when all said and done. All right, so there you guys go. Chapter 5 is over, so hopefully you enjoyed this last and final lesson, and hopefully you learned a little something. But if you have questions, just ask one of your teachers, come to us, tutoring, whatever you need. But we will talk to you later. Thank you.